I hope it's been recording this. Otherwise, we have to rely on the Brightspace recording. And I hope the Brightspace recording is downloadable. Otherwise we don't have this. Well, we can still watch it on Brightspace, but that's kind of... So, let's suppose that we've taken some edges so far. These are the edges we've taken. So this is our forest at the moment. And S extends our forest after I steps. Right? Yeah, actually that's a bit too path-like. Let's make it more of an interesting tree. Okay. So, this is a tree. It doesn't contain cycles. So the red lines are what we've taken so far, and the black lines are what S also takes to extend our solution into a tree. So, we consider some edge, and we take it, and S doesn't. So remember what I said about a tree on n vertices contains n minus 1 edges. So if we take the edge, the I plus first edge we consider, and we add it to S's, so to S, so let's suppose this is the I plus first edge we consider. You can see that this is blue and these ones are black, right? No. Okay. Better? Green? Okay. No. No, you can't see the green. The difference between green and black is not visible. Can you see the green line at all? Okay. So it's going to get bigger. So, we have so far, we have taken some edges, and S extends this by taking some more edges. Okay, now can you, the red lines, the black lines. Okay, so now, maybe what we would take, this is S, and the red lines are what we've taken, and we take the next edge we see, maybe it's this one. And S doesn't take that. So, S doesn't take that, but S has a spanning tree, a minimum spanning tree, and so if we take the edge that we would take in the I plus first edge in our order, and we insert it into S, then it's not a tree anymore, because now it has n vertices and n edges. So what that means is our edge creates a cycle in S. Okay? So, but the thing is, so consider just this cycle. So some of the edges on that cycle may be things we've already taken, but our solution, our sub-solution doesn't contain a cycle, right? Because we can take the I plus first edge, and we take it because it doesn't create a cycle. So that means there is some edge on this cycle that we didn't take. There is some edge that S takes that we have not taken so far. In this case, this one, this black one. So, if we take that edge and we remove it, the graph remains connected. Why? Because we can get from this end, if we didn't have the green edge, then we need that edge to get from here to here, or here to here, or wherever. But if we put in the green edge, we can still get from this endpoint to this endpoint by going around and over the green edge, right? So if you have a cycle and you take an edge out of it, you're not disconnecting anything. So that means we can take S's solution, add our edge, it creates a cycle, find some edge in that cycle that S has that our subsolution doesn't have, take it out, and get a tree again. Now, what can we say about this edge versus this edge? In particular, what can we say about the cost of this edge versus the cost of this edge? Anybody? Can this edge be cheaper than this edge? Have the same weight? Yes, because if this edge were cheaper than this edge, we would have considered this edge first, and we would have taken it. It's heavier or it's not lighter. It's not more expensive. So if we take S, we add the edge we take on the I plus first step, it creates a cycle, we find an edge on that cycle. There has to be one that is in S but is not in our subsolution so far. And then we take it out, the total weight of the total cost of the tree does not go up. Okay? So that means that on the this now, what do we call this graph? Where we took S and we put in what we take on the I plus first step, and we throw something away. That's an exchange. It's an exchange argument. What do we call this graph? Anybody? Yes, S prime. This is our S prime. We claim that after I plus first steps, our subsolution can be extended to an optimal solution S prime. So if S agrees with us on the I plus first step, great, it can be extended to an optimal solution, which is S prime, which is S. S cannot we cannot throw something away on the I plus first step, and S takes it, because we only throw things away if they create a cycle with the stuff we already have. S has everything we already have, so we create a cycle in S. So the only way there can be a difference is if we take something and S doesn't, but in that case we can take S and do this exchange and we get another optimal solution S prime, which extends now everything we took even up to the end of the I plus first step. Okay? So that answers the question from a few minutes ago. Does this always give us a minimum spanning tree? And the answer is yes, because by induction on I, when we start, we haven't made any mistakes. And if after I steps we haven't made any mistakes, on the I plus first step we don't make a mistake, therefore we don't make a mistake ever. Okay, we end up with a minimum spanning tree. Okay? Good. How much time do I have left? Any questions so far? No? So now so that's the proof of correctness. Kruskal's algorithm, proof of correctness. Prim's algorithm. Prim's algorithm is a bit different. So let's do the same graph. Maybe it would be faster for me to rewrite this. Okay, so now remember in Kruskal's algorithm we sort of start out considering that everything is a little tree by itself. Prim's algorithm, we don't do that. This is a G. Okay, can you still read this? Could you read this in the beginning? Maybe. Okay, so Prim's algorithm, remember we were talking about paving roads. In Kruskal's algorithm, in order to sort of pave the roads that way, to take the edges in the order of Kruskal's algorithm, you sort of need to have little road building workers at every town. Well, suppose that now you have like a, I don't know, bulldozer, something you can use to pave roads, road paving machine. And you have it only at one town, right? You're trying to save money. You've only rented or bought one road paving machine, and you have it somewhere. So now you can only, and your road paving machine is you bought the cheap road paving machine, so it can't go over unpaved roads. Okay? So you can only add paved, you can drive your road paving machine around paved roads, but you can only pave roads that are incident to towns that you can reach by paved roads. Okay? So this is weak motivation for Prim's algorithm. Where do we want our road paving machine to be located initially? What's a good starting point? Which town? Between A and I. Anyone? Random choice. Yeah, anywhere. Doesn't matter. Has to work from anywhere. Where do you want it to be? F or H? Okay. F said first, okay, let's put it at F. So, F, where is F? So what Prim's algorithm does, it starts with a tree consisting of one node, which is here, which is F. And then it looks at all of the edges incident to its tree, and it adds the cheapest one. So it adds 2. Okay? And now it looks at all the edges incident to this, and it says, okay, so I can take 1 or 6 or 4 or 14 or 10. What's the cheapest edge that I can reach? So now my tree includes G. What's the cheapest edge I can reach on any of these? H, yes. So now that adds candidates 8, 11, 7. What's the cheapest edge I can add incident to this tree? I, yes. Really? What about this one? C? Yes, sorry, that's a 4. Okay, C. Yes, sorry, that's a 4. Now, cheapest edge. Okay, so this is hard to read. So it's the cheapest edge is a 2. And then here, oh, sorry, I should have said it takes the cheapest edge as long as it doesn't create a cycle. Find the minimum weight edge and transfer it to the tree. Yes. That's how it works. From Wiki. Okay. Right, okay, so far I agree with Wiki. Okay, so, what's the cheapest edge? Cheapest edge, 10, 14, 7, 8, 8, 7, 11, so it's a 7, I think. And then it's, well actually this is where we can get a difference. Because it could be 8 or 8. Right, so this is going to make a difference. Because if we take this one, then we'll take this edge, and we won't take this one. If we take this one, then we take this edge. Okay. Which do we like, HC or BC or AH? Vote. Okay, not voting. BC, okay, BC has it. BC, we take this one. So now our tree is like this. Now the cheapest edge is this. And now the cheapest edge we can take is this one. Okay? So this has a nice property that it's always a tree. Right? So in Kruskal's algorithm, it's a forest, but this is always a tree. Why is the proof of, so that's Prim's algorithm. Please remember Prim's algorithm. It's legitimate material for quizzes, exams, whatever, except if I ask you, you don't have to memorize it because you'll have take-home exams. It's apparently on Wikipedia. So I have to come up with harder questions. So, no, I wasn't going to ask you just for Prim's algorithm anyway. The proof of correctness for this is a little bit trickier. So I should go a little bit faster. Maybe we don't get a break in the middle. So the proof of correctness here starts the same way. I mean, before we take any steps, our empty subsolution can be extended to an optimal solution. Yes, that's true here. Assume that after I steps, our subsolution can be extended to an optimal solution S. Yes, still the same. And we claim that after I plus 1 steps, our subsolution can be extended to an optimal solution S prime. Yes, we also say that, but the exchange argument is different, right? And it's not so easy. So now with Prim's algorithm, we always have a tree. And then, suppose that after I steps, S extends our solution so far to a minimum spanning tree like this. Okay? So, again, if on the I plus first step, we consider an edge and, well, we don't really, yeah, we can consider edges, we also consider edges and throw things away. I was skipping over that a bit. We consider an edge, if we throw it away, then S cannot, so if S agrees with us on the I plus first step, then fine, S can be our S prime. If S disagrees with us, it could be that we throw something away and S doesn't, but that can't happen because if we throw something away, then S cannot take it because we only throw it away because it creates a cycle. So that's why, I mean, we're considering things in order. Okay, I have to, it's on Wikipedia. You can read about it there. But, I want to get to the implementations. These are cool. So what can be different? Well, S, take something, and S says, no, I don't. For example, we take BC, and S says, oh, I don't like BC. S contains AH. So S would look like, instead of having A, B, B, C, it would have like this, right? And then the rest could be the same. So, how do we argue that if we take something, and S says, no, I wouldn't take that edge, I would take this other edge. We want to argue that we can still take S's solution and change it into an S prime that extends our solution. So, for example, if we take, well, suppose we take, on the I plus first step, we take this edge. Can you see this? Okay. Can you see that? Good. Okay, so this gets a little bit trickier than Kruskal's algorithm. Again, we have the solution S. We say the only way S can differ from us on the I plus first step is if we take the I plus first edge we consider and S doesn't. So let's say we take that edge and we add it to S. This will create a cycle. Okay? So now, this cycle, it will create a cycle. But now, the thing is, there could, for Kruskal's algorithm, we could say that any edge on that cycle, which we haven't taken so far, so in Kruskal's algorithm, any of the black edges had to be heavier or not lighter than the green edge. But now, that doesn't have to be true, because, for example, here, when if S takes this edge, and we take this edge, it's not true that this edge, A, B, this is 4, and we took 8. It's not true that all of the black edges on this cycle are heavier than the edge we just took. Because there could this edge, we weren't considering this edge. This edge could be lighter than this one. We couldn't consider it yet because we couldn't reach it. We're only considering the edges that are incident to the tree T we've built, to the tree we've built so far. Okay? But now I think I asked this on a quiz in the fall semester, which was very cool. But we can say there has to be some black edge on the cycle that is cheaper or not, not cheaper, that is not cheaper, that is at least as costly, at least as heavy as the edge we take. Why? Because the cycle includes stuff that's not in our tree so far, so it leaves the tree, so the red tree, it has to leave the tree, and it's a cycle, so it has to return to the tree. Okay? And that edge, so it has to have an edge, this green edge we take that leaves the tree, and the cycle has to have another edge that comes back. Why? Because this end is in the tree, and we have to be able to go from this end and cross this edge and go around and get back here again. So it has to have some edge, like this one, that is not in the tree and connects to the tree, is incident to the tree. So in this case, if we took this edge, if S included this edge, so we haven't taken this edge before, then if we add this to S, it creates this cycle. Okay, this is a bit fuzzy, but so in that case, we would have and our green edge is here. Okay, so this would also be black. It doesn't actually matter. This would be black. All of this more expensive stuff would be black. Okay, like black. And then this would be black. And this would be black. Can you see this? Yes, okay. So now if we add this green edge, it creates this cycle, but there has to be, so this green edge leaves the red tree, but the cycle has to come back into the red tree, and so this black edge, it has to have a black edge that is incident to the tree. This black edge cannot be cheaper than the green edge. Why? Because it is incident to our tree so far. So we do consider it, and we don't consider, so it is in our, at the things we can consider at the I plus first step, that edge is in there, and we don't consider it next. We take the green edge. So that means that it can't be that this edge is cheaper, otherwise we would have taken this edge. So therefore, we can put the green edge in and take this, there is a black edge that we can take out that is not cheaper, and so this creates, this is again a tree, the cost doesn't go up, so again we get a minimum spanning tree, and this is S prime, okay? Good so far? Good. Okay, so how much time do I have? I have 20 minutes to talk about, okay, that's possible. So, why do you need to know two minimum spanning tree algorithms? So, as I was saying, I mean, you can use Kruskal's, for example, Kruskal's is, you can use Kruskal's in a distributed system where everybody is sort of trying to do things in parallel. Prims you can use if you have only one road building machine. But there's a trick to Kruskal's that only comes out. Did anybody? Do you think you could implement Kruskal's algorithm? So let's see the list. Who thinks they could implement Kruskal's algorithm? Hands up. Okay, maybe you can, but not with the data structures you've seen so far. Unless you saw more fancy data structures than the people in the fall semester did in their version of 2110. Why? Because Kruskal's, remember in Kruskal's I was going around saying, okay, so you've sorted the edges. You can sort things. You know how to sort things, okay? So you sort the edges, fine, you can do that. And now I'm saying, so you consider this next edge. Does it create a cycle? Well, how do you find out if it creates a cycle? So in Prim's algorithm, it's easy to tell if it creates a cycle, because whenever you add a vertex to your single tree, you sort of mark that vertex. And then if you want to know if an edge creates a cycle, you just look if its endpoints are both marked. Okay, so that's easy. But in Kruskal's algorithm, you have a lot of trees, and you want to know if, when you look at an edge, are its two endpoints in the same tree? That's not so easy. I mean, you could do like a breadth first traversal from one of the endpoints and see if you get to the other endpoint. But that takes like linear time in the size of the component that you've built so far that contains